Okay, good morning. So, as you can see, there's a little joke on the board. This might be the most interesting thing in the lecture today. I apologise for that in advance. There's a serious point to it, which is to remind us that logic is not unrelated to pedantry. So logic is obviously the subject of logic. Pedantry, as I think I've already mentioned, is being pedantic, which is if you're pedantic, you're very, very fussy about the precise meaning of things, and everything needs to be exactly correctly stated. And obviously logic is a little bit related to, it's about formalism, how we express mathematics in a precise way. And logicians can be a little bit pedantic about how they use the syntax that they have in logic. So I thought this was, Sergio sent me this, Sergio Cavallo, a couple of weeks ago, so thanks to him for this. I thought it was appropriate for this lecture because today what we're going to be talking about is syntax. We're not going to need the screen, so I shall stop sharing here and turn the projector off. Hang on and get everything working right. Hang on. Something's a bit funny here. I'll just pause the recording while I get things, if I can. Okay, so today's lecture, as I've said, logicians can be very pedantic about meaning, and one thing they can be particularly pedantic about is syntax. And so, I mean, my approach on this course is to hopefully not be too tied down to being very precise about syntax all the way through the course, but we have to get over some initial hurdles and deal with some important aspects of manipulating logical syntax. And what I've decided to do is put all those things into today's lecture. So today's lecture is going to introduce a lot of important considerations about syntax, which once we have them, then we can just use them and we won't need to worry about them so much in future lectures. And from next week's lecture, we're going to start with what I consider the interesting technical material of the course. And today we're going to do necessary preliminaries, which are going to be important for the rest of the course. So what I'm calling this lecture is syntactic manipulation. So as you know, manipulations are ways of handling something so that you move it around and manipulate it. So change its form by reshaping it. And we're going to be considering ways we manipulate syntax. The syntax are the terms and the formulas of first order logic. But another nice way of thinking about this, which is also then a good metaphor for how to think about this lecture in the context of the rest of the course. There's a famous French logician called Jean-Yves Girard, who invented something called linear logic in the 1990s. That was a very popular subject in logic for a long time, and people still work on it. He had a nice phrase about syntax. He called it the bureaucracy of syntax. And that, I think, is an appropriate way of thinking about the role syntax plays in logic. It's like a bureaucracy. Bureaucracy is never an easy word to spell, even for a native English speaker, probably because it comes from France. I mean, not exactly this, but it's the French root. I know we've got some French people here. So as we know, bureaucracy is a blight on all of our lives. It's not a pleasant thing that we have to deal with, but we all have to endure it. And in some sense, syntax plays the same role in logic. We have to have syntax. It's the way we write formulas, and we have to know how to manipulate syntax. It's tedious and frustrating, but it has to be, we just have to accept it and allow it not to affect the rest of our lives too much. So today is a lecture about bureaucracy, if you like. I'll try to make it as interesting as I can. So I'm going to start with a worked example, and apologies if this seems to be going very slowly, but there are points I want to make through it that for some people I think will be useful. So I'm going to start by recalling the sentence in the signature. So this is something from the first lecture. There's a signature that had plus, and so the signature of a ring, if you like. So with the addition and multiplication and the 0 and the 1 operator, expressing the twin prime conjecture in number theory. So where we were interpreting variables as ranging over natural numbers. So expressing the twin prime conjecture. The very famous conjecture in number theory that people believe is true, but that's why it's a conjecture that nobody has been able to prove. And it's something people are actively trying to work on. Well, they have been for years, but recent progress has been made towards approximations to this. Anyway, they were writing it as for all x, there exists a y greater than x, or this is one way of writing it, how one would often write it, such that y is a prime and y plus 2 is a prime. I might not have written it exactly like that before, but in future, I will tend to write things exactly like this, where here we have a quantity. So this is not strictly a formula in our signature over in the signature we've got with addition and multiplication 0 and 1 as written. I mean, it is a formula, but as written like this, it's not a formula. It's a formula because we had a more complicated formula for being a prime, and here we're sort of expanding this using the formula for being prime. And also here, the way I've written it now, I've written a quantifier that has bound in it. We've got a lower bound on this quantifier. And again, we did not have bounded quantifiers strictly in the syntax. But the point is that all this can be interpreted in natural ways in the syntax that we have. And if we wrote this formula out in full, which I'm not going to do, it would be a much longer formula. And there are two particular things I want to explain. So one is how we're going to write bounded quantifiers and what they mean. So, well, this is how we write them, but how we expand them in general, that's something that's going to be very useful in this course. So that might seem the more interesting one, because the other one is just what we mean when we say prime y plus 2. So you might remember we had a formula stating that a variable x was prime, and here we're saying that y plus 2 is prime, and you can just imagine, well, okay, what we're doing here is we're using the complicated formula for x is prime, and in place of x, we put in y plus 2. And in fact, that's what we're doing, but the operation of putting y plus 2 in place of x is an important operation in logic. It's called substitution. We're changing the underlying formula we started with that had an x in, we're putting y plus 2 in. It's actually not a terribly simple operation. It looks, you think it might be simple because you're just putting one thing in place of another, but it's not that simple. So one of the things I want to do today is address that operation. And as I say, this is going to be the only lecture on this sort of level of syntactic detail, but at some point on the logic course, it has to be done. Better early on than later on, and I'm just trying to get the camera to, I think these batteries are Oh, well, never mind. That's better. Right, so first we'll deal very quickly with the bounded quantifier. So we're going to use bounded quantifiers in situations in which we have a signature that has an order relation on it. Actually, you might remember in this signature, the order relation is itself not a primitive. We can see it's not in the signature, it's a defined concept, but it doesn't matter if it's defined or not, we still use the same abbreviations. So, so bounded quantifiers are useful abbreviations. So we're going to have quantifiers like there exists an x less than some other value. Now, what's the appropriate thing to have for the other value? Well, the syntactic construct we have that gives us values is terms. So we have to have a variable here because it's what we're quantifying over. So there exists an x, it only makes sense to have a variable there. But in general, if we want to say there exists an x less than something, we give ourselves the most general scope here to have something, to have the bound, to express the bound in the best way we can. So we could in general have a term here. So in general, we'll often write formulas of the form, there exists an x less than ta. And what this means, so this abbreviates, there exists an x is less than t and a. And also we might have for all x less than ta. You have to be a bit careful in the abbreviations. I mean, because if you think about the meaning here, if you want to say for all x less than t, a holds, I mean, there should be things that are familiar to most of you, but the correct connective to have here is not conjunction. If you think about it, you'll see that's saying the wrong thing. What we want to say is for all x, if x is less than t, then a holds. So we use an implication there. And similarly, we might say there exists an x greater than t, a. So even if we have just a less than symbol in our signature, we still have an implicit greater than, which is simply less than the other way around. We might not ever write that in formulas, in the main part of a formula, but it's very useful to use that for quantifiers, because if we want a lower bound for a quantifier, it's natural to use it in the greater than orientation. So I'm going to put that as an abbreviation for what this is saying. So this abbreviates exists an x, in this case t is less than x and a. So you see, one can just use the other orientation there. And lastly, for all x greater than t, a, and that abbreviates, obviously, for all x, t is less than x implies a. Okay. So hopefully that's all very simple. There's one thing to say here, and further thing, just my notation here, I'm using a capital A and a lowercase t. And what do I mean by that? Well, here I'm giving you a pattern. This holds whenever we can write this, whenever we have an actual concrete term, like something like y plus z times 1. Well, yeah, I mean, that would be okay. That's a syntactically okay term. And we have an actual concrete formula A. And I'm writing it in this way, sort of schematically, to say we have this abbreviation for any term t and any formula A. And I'm often going to use this sort of notation. So t and A here are called meta variables. They're not variables in the logic like x, y, and z, ranging over elements of a structure. They're variables that we're using for our notation to express patterns. So this pattern, a formula, stands for some formula of the form, where this is a term and this is a formula. So these are meta variables, and in general, I'm going to often use this kind of syntax. So we use these things in general. I'm going to use letters like S, T, and U will range over terms. So if I want to say this is a term, in general, I just typically use a T or something. So these will range over terms from our signature. And I'm going to use just simple capital letters from the beginning of the alphabet, typically, for formulas. Okay. So, for example, we can express logical laws using this kind of notation. So the meta variable notation allows us to, for example, express logical laws. And we're going to cover logical laws and reasoning using logical laws in much more detail when we look at proof systems, which I talked a little bit about last week, about the idea of having proof systems. But just an example of that. So, for example, using this notation, we might observe that following schema for formulas. A schema, in the sense, it's not a single formula. This is a pattern for formulas where you have a formula A, and in disjunction with its negation, any formula of this form is always valid. So an example, such a formula would be twin prime, that's this sentence here, or not twin prime. This is always valid. It's always valid because the logic in this course is what's called classical logic, the usual logic of mathematics, because we have classical logic. And just to say, as I think many people in this room know, there are other logics, constructive logics or intuitionistic logics in mathematics, in which this formula is not considered as always being valid. This is called the law of the excluded middle. Law of the excluded middle. It's very but for any statement, it is either true or its negation is true. There's no sort of, you're excluding a middle because there's no kind of in-between possibility. There's no sort of fuzzy possibility in the middle. That's the, I think, originally in Latin it was called something like tertium non datur or something like that. People still refer to it like that sometimes. It's abbreviated LEM. Anyway, the point here is just to illustrate this kind of notation, how we can also state things like valid principles here. Right, so I now want to go back to the other issue I was talking about, the substitution issue. So this means substituting y plus 2 in the formula expressing prime. And as I said, that's a little bit more complicated than you would think at first principle. Initially, you might think that that should be a very simple operation, but I'm going to try to explain how it's not as simple as you might think. But hopefully a good way of thinking about it so that you don't need to worry about it too much. Because it's actually the sort of thing, if you worry about it too much, you can get headaches from that. And it's good to just have a quick way of being able to deal with substitution. So I'm going to try to give you that. So let's go back to twin prime. So twin prime. So by twin prime, I mean the sentence expressing the fact that there are infinitely many twin primes. So this is now expanded to, we've expanded out the bounded quantifier. So it's now expanded to, for all x, there exists a y, x is less than y. That's the bounded quantifier here, expanded out, and prime y and prime y plus 2. So this is still not a formula in our signature because less than is a defined concept and prime is also a defined concept using a more complicated formula. So, so let's expand it as far as we can be, as far as we can tolerate. So here, x less than y, as you might remember, our variables are ranging over natural numbers. So x less than y, that abbreviates that there exists a z such that y equals x plus z plus 1. So recall. Yeah. And prime y, well, we had I think I'm departing from my notes a little bit here, so let's hope everything's going to work out all right. Sometimes it does, sometimes it doesn't. I think this is a better way of saying it. So I think in the first lecture, the formula I said for giving prime, I think it was prime x, but in any case, I'm going to define what it means for x to be prime here. So prime x is the formula so prime x is not the case. It's not the case that x equals 1, and for all y, for all z, if y is x times z, then if x is y times z, then either y equals 1 or x equals 1. Sorry, z. Thank you. This is not to do with partly from my notes. This is just early morning. So my brain is not quite yet boiled this morning. Okay, so we would never. Okay, so let's now think what prime y plus 2 means. So we could look at prime y, but prime y plus 2 it is more complicated. Prime y plus 2 is, well, we want to express that y plus 2 is prime. So we somehow want to replace the x in here with y. But with y plus 2, which is y plus 1 if one's writing things out in full. So prime y plus 2 in full would be not y plus 1 equals 1, which of course it's never going to anyway, so that's always going to be true in the model. But still, we're just getting a formula out of the operation of plugging y plus 2 in here. And your first attempt at saying it here, for all y for all z, is again we replace x with y plus 1, we'd be saying y plus 1 equals y times z implies y equals 1 or z equals 1. So this would be a first attempt, but just hands up if you can see what's wrong with this.
We didn't change the y.
Yeah, so the problem is we substitute the y in here, the y, we want to say y plus 1 or y plus 2 is prime. If we plug y plus 1 in here, then we've got the problem that we're no longer talking about the y that we want to talk about because we happen to be inside the scope of the quantifier that's variable is y. So you can think about what this means if you want in your own time, but this formula is completely not the right formula for saying that y plus 2 is prime. So I don't want to rub it out, but it's wrong. So let's at least note that it's wrong on the board. I'm running out of space at the bottom there. So let's put it the correct formula here. So the correct thing to do is, because we're substituting something with a variable y in, you might remember, and it's very intuitive, it does not matter what you call, in general, a bound variable. If you say for all x something holds, that's the same thing as saying for all w something holds. It doesn't matter what you call a bound variable. But it is problematic if you want to talk about a y in the outside world, a y that you've actually got some reference to, and you've got a quantifier that uses the same name. So because it doesn't matter what names you use for bound variables, you rename the y here to avoid this clash. And then, so we might call this y w, and then we can plug in the y plus 1. So the correct formula is not y plus 1 equals 1. So I'm already abbreviating things a little bit. I said I was writing it out in full. Plus is a binary operation, and I'm avoiding the bracketing, but never mind, there's a limit even to my pedantry on this. So if we renamed this y here w, then all the y's in this formula would be w. It'd still say x is prime. Then we can substitute the y plus 1 in. So a perfectly legitimate substitution is this. Y plus 1 is w times z implies w equals 1 or z equals 1. Okay, I hope that's right. If it's not, please. If it's not, please let me know. But in any case, assuming it's right, I'm going to give it a green tick to emphasize that this is the correct substitution and this is not. Notice from this, just one little fussy thing. In a sense, the substitution is not uniquely determined because instead of w, we could have chosen v or any other variable name different from y and different from z, and it would have been all right. So it's not uniquely determined, but it's determined up to preserving the meaning of formulas, because it doesn't matter what variable name we use here. There's actually a notion of equivalence of formulas that comes from the lambda calculus called alpha equivalence. For those of you who know about lambda calculus, the substitution is uniquely determined up to alpha equivalence. But that's a side remark just for those who have the context to understand it. It's not important for this purpose. Okay, so now having looked at that little example, we can look at the general substitution operation. So in the example on that board, we were substituting y plus 2 for x in the formula for being prime. So for the example substitutes, and this is a technical word in logic, so it's an informal word we're replacing, but it's a technical word as well. It has a precise meaning, which is essentially the operation I showed you by example there. So it substitutes the term. So in general, we substitute a term. There we were substituting the term y plus 1 or y plus 2. I just want to emphasize kind of the primitive form, although still I haven't told you how it's bracketed, but it doesn't matter. So the term y plus 1 for the free variable x in the formula I'm writing prime x, okay? So let me say in the formula prime x. So here the brackets is just saying it's a formula prime, and I'm just, with the x, I'm just saying we're kind of highlighting that it has, here, there is the formula here. We're highlighting that it has a free variable x. So remember, a free variable is one that does not occur within the scope of a quantifier that names that variable. We had that in the first lecture. And in fact, then, this is an instance of the general forms of substitution. We're going to have, we have two general forms of substitution. So the one that we're illustrating above. So let me see what notation I'm using. So I hope this is consistent with the LaTeX notes. I should have double checked. So as long as it's consistent with the LaTeX notes, at least for today, I'm going to write it like this. So this means exactly what we said above. So this is, I should have written it more on the left, but this is substitute the term t for every reoccurrence of the variable x in the formula A. So I say reoccurrence because it's possible to have a formula in which the same variable occurs both free and bound. For example, we could have x equals 0 and for all x, x equals y plus 1, for example. And then this occurrence of x is free, and this occurrence of x is bound here because it's inside the scope. Okay, so that's why the word occurrence comes in. And in order to define that rigorously, and it's also anyway useful, so let's put an S here. So this is a term. We're also going to have a notion of substituting a term for a variable x in another term t. So this is substitute the term t, the term t for every occurrence of x of, I'm not going to say the variable x again. So for every occurrence of x in the term s. Okay. So we always substitute a term for a variable, and we can do that in a term, in another term, or in a formula. Okay, one question here. Why do I not need to say free occurrence of the variable x in the term s?
Because it's a term.
Because it's a term. But it's a term, not a formula. So in particular,
There's no quantifier.
There are no quantifiers, so it does not make sense to talk about bound variables in a term. Okay, every variable in a term is free because you cannot. So this isn't always true for all logics. One can have other more powerful logics with more complicated ways of forming terms, and then you can have bound variables in terms. In first order logic, you never have bound variables in terms. And the other thing to warn you about is this notation. Well, first, it's very standard, but on the other hand, there are hundreds of notations for substitution, and they're not all consistent with each other. Some people write exactly the same notation, but they have the term that you're substituting for on the right and the variable on the left. So it's very confusing if people don't explain what they're saying. If you get substitute x/y, you don't know which way round it is unless someone's carefully explained. And there are other notations people use as well. So there are lots of notations. This is very standard, but sometimes it's used in a different way. So just be, if you're looking at textbooks, just be warned about that. I don't know, the textbook I recommend for this course, the main one, I've forgotten the name of the guy, the German guy, a very good textbook. I don't actually remember what his notation for substitution is, I'm sorry. But I recommend that book. So we've just got time to squeeze it in. So based on this example, but there are two ways I could deal with substitution now. So now hopefully you're going to be pleased. I'm going to not go for the most pedantic of them. The most pedantic and most precise is to define substitution, giving it an inductive definition on the structure of a term, saying, this is what you do for a variable. This is how you build it up if you build a term via function symbols. Actually, that's easy. But then you have a more complicated definition for formulas, where again, it's on the structure of formulas, where you say, this is what you do if you're a term, or if you're an atomic formula involving terms, and this is how you deal with the connectives, conjunction, disjunction, and so on. And these are the two complicated cases. This is how you deal with the quantifiers. And these quantifier cases are actually very tricky to get right because of this problem of renaming variables. And I have seen, maybe not in famous textbooks, but I've seen many examples of people that failed to get these right. So it's a bit thorny to do it. Thorny, like a rose bush has lots of thorns, it's prickly. It's a tricky, but we use it metaphorically to mean it's a tricky thing to get right. So I think I would be able to get it right if I did it, but I'm not going to put myself on the line here because I'm not going to do it that way. I'm certainly aware of the issues. For people that are interested in programming languages, if you write compilers for or interpreters for functional programming languages, you get exactly the same issues in defining substitution for the evaluation of lambda terms, for example, if anyone's ever done that. Lambda terms being lambda calculus that's used in functional programming, you get exactly the same issues there. And if you're writing a compiler or an interpreter, you have to get it right. Otherwise, the program doesn't work properly. But anyway, the way I'm going to deal with it is along the same lines that we had here. So I'm going to give you the general recipe, which is in practice, the use. If you want to work with logical formulas in practice and do substitutions, this is what you do. So the general algorithm, not defined in such a precise way, giving an inductive definition case by case on the structure of a term and formula. The general algorithm for calculating so the substitution of a term for a variable in the formula A is exactly what we did in the example. So first, rename bound variables in A so that they differ are different from all variables in T in this case, we were substituting y plus 2, that was our term T, for the variable x. So we had to name the bound variables in the formula so that they were different from the variables in y plus 2, and the only variable in y plus 2 was y, so we just had to make sure there were no bound y variables in the formula. You actually also have to make them different from x in general for things to work, for this particular algorithm to work. So they should be different from x. Remember, we're only renaming the bound variables. So this only occurs in the case that we have x appearing both free and bound. That's the only problematic case here. We make sure that doesn't happen. So that they're different from x and from all variables in T. So that's the first thing you do. And then second, once you've done that, it's easy. You simply textually replace. So literally just take every occurrence of the variable x that's left and simply put T in its place. Okay? So simply second replace. Let me even say textually replace. Textually replace all remaining occurrences of x, which were the free ones, of x in A with the term T. Okay, and that's the algorithm. One of the comments, I haven't given you an algorithm for substituting the term T for a variable x in a term S. So what would be the algorithm in that case? Anyone got an idea?
Just the second part.
Yeah, so it's only the second step. So you can write that down if you want to. But it's literally, so it should be written down, but I'm just telling you. And you can write it down if you want to. But it's easy. You don't need to, because you don't need to worry about bound variables and variables. So the problem that occurred here when we substituted the y in this quantifier here, this is called variable capture. You think, so that's the technical term for it. So you think you're substituting a term with a y in, and that's supposed to be a free variable, but it gets captured by this quantifier here. So we need to avoid variable capture. And there is no problem of variable capture because the term S doesn't have quantifiers. So you can simply just do textual replacement here for the substitution. Okay, so that's taken us to 9 o'clock. So we'll have a pause to 9:15. I'll pause the recording. Okay, so in the first chart, we've finally got the definition of substitution in a practical form. That's the form that it makes it easy to use rather than the rigorous form, which would be to present it, giving a definition, defining exactly what you do for every instant, every case of a formula constructor, including the quantifiers. Anyway, you should get essentially the same thing in the end. So that's the syntactic side. One of the important things about logic is how syntax connects with semantics. So how the syntax of what we write connects to the meaning in a structure. Terms denote elements of the structure, formulas properties of structures, as we've already said. So here we're changing, by substitution, we're changing a term from one term to another by substituting a variable in it. And here we're changing a formula by substituting a term or a variable in it. So in both cases, we're changing the term itself, S, and the formula itself, A, and therefore changing the meaning of the term and the formula. We have a new term with a different meaning. But substitution is a nice operation. It's an operation that has itself a sensible meaning, and that's reflected in the fact that we can look at substitution from the viewpoint of semantics and see how it alters the meaning of a term and a formula. So I just want to state this. I'm not going to prove it. But this is something that it's a good exercise for you to think about why what I'm about to write. It's true. So we need to go to another board. But in particular, I think even more than thinking about why it's true, to understand, I mean, I'm going to explain it anyway, but to understand what the next, I'm going to call it a lemma, what this states. So I'm going to call this the semantic meaning of substitution. Now, I said to think about it for yourself. I'm also going to talk you through it, but it's a good idea to reflect on it a little bit. So one could, there's always a question: do you call things a theorem, a proposition, a lemma? And somehow, depending on the use, this is certainly not a theorem. It's not something that's not going to be like the completeness theorem or the incompleteness theorem. It's not a major result of logic. It could be a proposition. It's stating an important fact. But I think it's fair to call it a lemma here because it's really something that one uses a lot. One does substitutions and one wants to say what the substitution amounts to in interpreting the formula or term in a model, and then we use this lemma that tells us the answer. So as you know, lemmas are results that are used for other results, and this is certainly a lemma that gets used a lot. And what it says is, well, we want to say how the meaning of the term that we get by, we're going to do one for terms and one for formulas, how the meaning of the term we get by substituting another term t for the variable x in the term u, how that gets affected by the substitution. So the meaning of a term as an element of a structure that's given relative to an assignment or environment, as you will remember, that maps every variable in the term to maps every variable to an element of the structure. So can we say something about this? Well, it's very intuitive if you have the right way of thinking. You want to say what the meaning of this substituted term is. So on the outside of this term, we've got the term structure for u, and then wherever there was an x in u, we've replaced that with the term t. So basically, the meaning of this term should be gained from the term u by looking at whatever the outermost function symbols in u are, and applying those recursively down through the structure of u until we get to constants or variables. But when we get to a variable x, we don't take its meaning under row. We instead take it's going to be substituted by t. So essentially we can get this by interpreting u itself in the environment that's like row, except we update the meaning of x. And I don't remember what notation I use. So the problem is I sort of flit around from one notation to another in my own work. Did I use this notation a few lectures ago? Yeah, so this might not be the same as in the lecture notes, I don't know. Anyway, what we do is we change the meaning of x in row to, we give it the element that's got from the term t assigned to row. So it's very intuitive because here we're replacing x with t. So in the meaning, we replace the meaning of x with the meaning of t in the environment. Okay? So that's the case for a term. And the case for a formula, well, to talk about the meaning of a formula, we talk about how the satisfaction relation is affected. So in a structure M, a substituted formula, we use square brackets for substitution. So the formula A with T for X substituted is going to be true in an environment rho. So remember, as I've said a few times, I write the row up here. Gregor's writing the row down there, which is actually more standard, but obviously it doesn't really matter as long as one's aware of the difference in notation or choice. So we want to say when this formula is true in the structure M, well, once again, this formula is the same as A, except that we've replaced the X's by T's. So once again, it's the same as asking for A to be true, as long as we make sure that X is assigned the appropriate value, which is the value that T has. So A is true in the environment row in which we assign the value of T in row. So in the environment we get from modifying the starting environment row by changing it to assign to the variable X the value of T according to row. Okay, so I think that's enough explanation of it. It bears thinking, as I say, it bears thinking about, and I encourage you to think about this. And as an exercise, to think about how you would prove it. And that's all I want to say about substitution. Okay, so for the rest of the lecture, I want to consider a general issue, which is now looking at the language we've got for expressing formulas and thinking about how we can simplify formulas in very many different ways, because for different applications, it will be useful to simplify them in different ways, such as putting them in particular, putting any formula into a standard form in which it's a formula constructed in a very specific way. And I mean, I think to see how this is going to work, it's better to just do the examples, and there are lots of different cases that we're going to consider, and the examples will talk for themselves. But firstly, before doing that, let's review our syntax for formulas. Although I'm going to add some more things to we already had the syntax in the first lecture for formulas, but it's going to be useful to have even more constructors for formulas than we already had. And it's quite liberal. I mean, some logic texts are very parsimonious. You have logic texts that only have the universal quantifier, negation, and implication, and that's all they ever have as their primitive symbol. Some are very parsimonious. I was quite liberal already in the first lecture. I put in a lot of stuff into the syntax. I'm now going to be even more liberal. So formulas, so the largest class of potential formulas I'm going to consider are, well, of course, the atomic formulas. So if we've got a predicate of arity K, then we've got atomic formulas formed from a predicate, equalities. And now I want to consider the propositional connectives. But in addition to the propositional connectives, I'm going to put in two what I call propositional constants. Sorry, we can view propositional constants as just like a term constant is a zero arity function symbol. A propositional constant is a zero arity predicate symbol. But these are special ones that have logical meaning, a determined logical meaning. So this is truth constant. The one, looks like a T, but in LaTeX that would be \top. And this is the false constant, which in LaTeX is \hot, or \perp, I think is another way of putting it at the bottom. So we have a true constant, we're going to have a true constant, a false constant, negation, conjunction, disjunction, implication. And another connective I'm going to add as a potential other connective in by implication. So this is by implication or if and only if. if and only if, or by implication. So I hope it's clear, this horizontal row is connecting to here, by implication. And by, I guess one would hyphenate that, by implication. Somebody can look it up on Google and see if it's hyphenated or not. It certainly has 2 eyes in it anyway. Yes, it's really not in the right place, is it? But anyway, there we go. And then we have the quantifiers, the quantified formulas for all xa and exists xa. So if we were defining the satisfaction relation in full, then we would have to define a satisfaction relation for true, it's always true. Satisfaction relation for false, it's always false. And the satisfaction relation for if and only if. So you can do that in your own time if you want to. But we're going to, in any case, in just a moment, eliminate lots of these connectives in terms of a very basic set. But we're going to see one can do that in very many ways. And it's going to be useful to have a general result that expresses that. So I think most of it will be familiar for you, but the interesting thing is to get a general result that expresses what one can do as sort of generally and concisely as possible. But beforehand, what I want to do is show that we don't need to have all the connectives. In fact, we can get away with very few. For example, just the ones I mentioned before, negation, implication, and universal quantification. That would be on its own a sufficient set of connectives for everything. So I want to show you can define some connectives in terms of others, and I'm not going to spend a long time on it. I just want to do things as concisely as possible, as I said. But before that, in order to motivate what we're doing, and also because it's a fundamentally important concept, it's going to be it's going to occur again and again in the course. I mean, just as a basic concept that one works with, I'm going to introduce the notion of equivalence of formulas, logical equivalence of formulas. Did I move the camera? No. So this is just a definition. We're going to say 2 formulas A and B. A and B are logically equivalent. But because it's logic, we don't always need to say logically equivalent, we'll just say equivalent. If for all structures M and for all environments ρ, interpreting the free variables, so if and only if for all structures M, for all environments ρ, A holds in M at ρ, if and only if B holds in M at ρ. Okay, so A is true, if and only if B is true. They're true in exactly the same basics. So it's a bit like, it clearly has some affinity to the notion of logical validity that we had last week. A formula is logically valid if it's true in every structure, so if it's in every environment. And here, formula need not be logically valid, but it's kind of exactly as valid as B is, so to speak. It's true in exactly the same instances that B is true. So equivalently, this holds if and only if formula, and this is a useful aspect of our if and only if connective. Of course, I haven't given you the semantics for if and only if, but I think you're all familiar with the connective if and only if. We're going to have its meaning in just a moment via an alternative route. But if and only if this formula is valid. As if you think about it, this formula being valid, that's saying this is true in all structures and all environments. And that is exactly the same as this statement here. So that's an alternative definition. Let's put the box here. That's an alternative way of defining the notion of logical equivalence. Okay, it's very important to understand this notion. So this is something else to, if you're a little bit puzzled by any aspect of it, think about this in your own time. Very, very important. All these concepts today, basically, it's all fundamental material that a good understanding of it is going to be important to the rest of the course. Okay, so now with the notion of logical equivalence, I now want to address the topic of, on the one hand, not needing all the connectives, and on the other hand, finding simplified formulas. Well, simplified formulas meaning formulas with a simple structure expressing properties. So first I'm going to address the idea that we don't need to have all the logical connectives or all the quantifiers. And this is the general notion here, is the notion of what's called a sufficient set of connectives. So the idea is we say, okay, we'll only give ourselves, say the ones I mentioned, negation, implication, and universal quantification. Is that enough to express all logical properties? Probably most of you know, and I think I've already said that in that case, that is enough. But that's not the only way we could cut down these formulas. So I want to state a general result that expresses nicely all the examples of being able to cut down the formulas that we're going to use in this course. So the general idea is that we do not need to have all the logical connectives. So we don't need all connectives, quantifiers, but there's a terminological issue here. But people tend to talk about connectives for these propositional connectives like and or implication, and quantifiers for the quantifiers. And if you want to talk about them all together, people often say logical constants. But I find that a bit of a heavy phrase. So I'm just going to say loosely connectives to mean sort of sufficient set of connectives means a sufficient set of connectives and quantifiers. We also might not need to have all the quantifiers. So the idea is to we show some can be defined in terms of others. So true, we can simply define as, so I'm going to use this three-barred equivalence. Now for logically, I didn't write it here, but this is logical equivalence as defined on the left-hand panel. So this is logical equivalence. So we don't need the true connective because if we pick some chosen atomic formula G, then we can obviously get true by, say, G implies G or not G or something. So G, a chosen, well, atomic formula, but it could just be a chosen formula. It doesn't need to be atomic. It's not involving true, but it could be atomic. And false, of course, we can eliminate because false is equivalent to G and not G. And by implication, well, the natural way of even understanding that is via a definition in terms of implication and conjunction. So it's easily implementable in terms of implication and conjunction, because that is simply the formula A implies B and B implies A. That's exactly what by implication means, an implication that runs in two directions. So those new connectives we added today, true, false, and by implication, are just easily implementable in terms of what we already had in lecture 1. So the next general observation is this, that if we have negation, then we only need one of the connectives. So we're now left with, we've kind of got rid of true, we've got rid of false, and we've got rid of by implication so far. So we're left with the negation. But the propositional connectors, we're left with negation, conjunction. So conjunction, disjunction, and implication. And if we've got negation, we only need one of those, and any one of them will do. So if we have negation, we only need one of the connectives. Connectives implies conjunction and disjunction. And we can do this because we can define each of them in terms of any one of the others. And the easiest way to see this is to give a sort of cyclic round of definitions of one in terms of another, that in terms of the third, and vice versa. And then by applying at most two of those, you can redefine any one in terms of the other two. So one way of doing that, let's start with the well-known definition of implication in terms of or. So A implies B is the same with material implication as it's called, as not A or B. One of the things that in philosophical logic, one puzzles over this for a long time in philosophical courses on logic, because it is quite an interesting idea that this should mean the same as implication. We're doing mathematical logic, so we shall carry on. So disjunction is defined, well, we can define that in terms of, so here we've defined implication in terms of negation and or. Disjunction can be defined in terms of negation and using one of De Morgan's laws. So it's not A and not B.
Excuse me, Professor.
Met De Morgan's laws before, so this is one of them. So we'll meet them again very shortly. And now I want to define conjunction in terms of, we want to make a cycle, and then using the cycle, you can, as I say, apply at most two of them to write any one of them in terms of any of the others. So I'm going to do conjunction in terms of implication and negation, and conjunction is the negation of A implies not B. Okay. And again, if we have implication, we only need one of the quantifiers. Sorry, if we have negation, we only need one quantifier, because again, we have well-known logical equivalences. So exists XA can be defined in terms of for all a negation using the duality principle, that there exists an X is the same thing as saying it's not the case that for all X, not A holds. Again, for people that are interested in remarks, it doesn't matter if you're not interested or you don't know anything about other forms of logic, but for people who are interested in remarks connecting other logics like constructive logic or intuitionistic logic, this is not a true equivalence in intuitionistic logic. Oh, thank you. And the same with universal quantification, but universal quantification is equivalent to the same duality principle. Then it's not true that there exists an X such that A is not true. So given all this, we can nicely write a nice table of sufficient sets of connectives based on what we have. So a sufficient set of connectives is just a small collection of connectives that suffices for expressing any first order logical property. So we therefore have, again, I'll write sufficient sets of connectives so we have, as long as we have negation, then in addition to that, we can have any one of conjunction, disjunction, and implication, together with one of the quantifiers. And I want to have it in this form because for different purposes in this course, you know, if you're expressing logical properties, it's good to have as many connectives as possible because you express things in natural ways using short formulas. But if you want to prove properties of all first order, if you want to prove something about all first order properties, then to give yourself as little work to do, you want to have as simple as possible a way of forming first order properties. So it's useful to have a small collection of connectives that gives you all first order properties. But which one is useful depends on what you want to do. So actually, for different purposes in the course, we will use different combinations of these connectives of our minimum set, but they will always be one of the collections that one gets from this proposition here, from this result of either minimum sets. As an interesting exercise for those who haven't seen it before, there are two definable logical connectives that are not the primitive ones. There are two possible ways of doing this. There's a binary logical propositional connectives that suffice on their own. There are exactly two of them. And as an interesting, slightly challenging exercise, you might know this, some of you, but anyway, to think about what those two connectives would be. And it's not natural. It doesn't lead to natural expressions of properties if one uses just the single connectives. But some people like it as there's this notion of Occam's razor in sort of philosophy in general, which is reducing any sort of set of concepts or something to the minimum necessary. And in some view, just having a single binary connective, you still need a quantifier, but just having a single logical connective as a kind of nice example of Occam's razor. The minimum set is just a single primitive logical principle. Okay, so this is getting rid of it's getting rid of connectives, but actually maybe a better way of thinking about it is getting by with as few connectives as possible. And now I want to start the last main topic, which is related to this, which is now putting formulas into simple forms so that if we want to talk about first order properties, then it will be enough to consider formulas in simple forms. And the first such form I'm going to consider is something called Prenex normal forms. I think we'll cover this just in time for the break. So Prenex or Prenex, I'm not actually quite sure how to pronounce it. Probably either is okay. It's It's not a word in everyday English usage. So a first order formula, I'm not going to bother to write first order formula. I'm not going to bother to write first order. Our formulas are first order. So a formula is in Prenex normal form. Prenex. Oops. So irrespective of the pronunciation, I should get the spelling right. The spelling is not controversial. So a formula is in Prenex normal form if it is of the form Q1x1. Well, I'll put in a 2 case here, Q2x2, ... Q, and this is the sort of thing where it's good to have the same letter as in the notes. So we'll count up to k here, Q sub k xk, B, I think I call it B, where these Q's here stand for quantifiers. I'm using the letter Q because they might be for all or they might be exists. So these are quantifiers. So we've got k quantifiers on the outside. And the important thing is we've actually put all the quantifiers in the formula on the outside. That's the important thing about Prenex normal form. So B is a first order formula that contains no quantifiers. It's built from atomic formulas. I don't have my list of formulas, but it's built from atomic formulas just using the propositional connectives. And such formulas are called, I don't need to define it because the descriptive name that tells you what it is, it's a quantifier-free formula. Okay, so basically we pulled all the connectives, all the quantifiers to the outside of the formula. And just to clarify what this means here, so here, in the general case, we've got a string of quantifiers, and here k is greater than or equal to 0. So in particular, this includes the special case, the trivial case where you have no quantifiers and just a quantifier-free formula. Such a formula factoriously counts as being in Prenex normal form. It's funny, sometimes Prenex comes naturally to me and sometimes Prenex. Anyway, so let's just clarify here, k is greater than or equal to 0. And Prenex normal form is useful for a number of purposes. We will see applications a bit later on. What's important today is the result. So this I'm going to call a proposition. Again, I don't think it's not the sort of result one would call a theorem. So it's the Prenex normal form proposition. Well, this says for any formula A, it basically says any formula is equivalent to a formula in Prenex normal form, but it's going to be useful to have a notation for that formula, so I'm going to just write it in a slightly more complicated way to give me that notation. So for any formula A, there exists a formula A, I'll just say superscript P and F in Prenex normal form such that it's logically equivalent to A. So every formula is equivalent to 1 in Prenex normal form. So that's an important result. So we've got 8 minutes to the break, and I think that's enough to give you enough of a hint of how to prove it. So there's the actual proof itself, which we'll come to. But before that, there's the reason that the result holds, which is really the more important part, understanding the key to the proof. And the key to the proof is certain laws that tell us about how we pull one quantifier out at a time, how we move it outwards in a formula from the inside to the outside, one step at a time. And these properties are called distributivity properties for the quantifiers, because they relate to distributivity properties in the algebraic sense. And let me try to move the camera. So we had distributivity properties for quantifiers. Over conjunction and disjunction. So something you should know, and it's easy to check yourself, so and also think about why this is true, is that existential quantification distributes in the best possible sense over disjunction. And existential quantification is kind of dual to universal quantification. Disjunction is dual to conjunction, and universal, excuse me, universal quantification distributes in the same sense over conjunction. It's very easy to verify these laws for yourself in terms of the logical meaning of formulas. The more tricky case is, what do we do? We've got an existential quantification over conjunction. Well, it's not the case that we can simply pull the existential quantifier out in this case, but there's one case in which we can do something. So this is the same as there exists an XA in A and B if X does not belong to the free variables of B. So I don't think I introduced this notation before, but I'm telling you here what it means. So FV of B is the set of free variables of the formula B. We're saying so this is just saying if X is not a free variable in B. Okay. So I don't want to write it down now. Hopefully you can write it for yourself if you want. And now we want to do the same for a disjunction here. And then we have exactly the same property, but we can again distribute we can put the universal quantifier just around the A. As long as X does not occur free in B. So we've got for B. Then if X, sorry, let's put that. So again, if X does not occur free in B. So these are important logical equivalences. From the point of view of Prenex normal form, what's important is kind of going from the right to left direction. And actually, the two important ones are the bad cases, this one and this one, because this tells us if we've got a disjunction or a conjunction, we can pull a quantifier from an inside formula and make it and put it on the outside. And that's giving us a way of pushing the quantifier step by step towards the outside of the formula. And if you iterate this often enough, then you're going to pull the quantifier all the way out, as long as the propositional connectives are just and or. Now it's not enough to just have and or, unless you make other restrictions, which we will do in a moment. But without even making other restrictions, we can prove the Prenex normal form proposition. Yeah, so let's do that and have a break. I don't think I want to give as many details as are in the notes. The proof of the TNF proposition. So to simplify life, we will restrict to a sufficient set of connectives using what we did earlier. So this is where sufficient sets of connectives are useful. We want to talk about general properties, but we want to have as few as possible cases to consider in our proof. So every connective or quantifier gives us a case, so let's have as few as possible. So we restrict to the sufficient set of connectives negation or an existential quantification for the input formula to the process, for the formula A. And we now need to define what the Prenex normal form of A is. So we simply define that as A, P, and F. Whoops, PFN, I don't know. P and F, Prenex normal form, is defined to be equal to, well, there's just going to be a lot of cases. So it's going to be A itself if A is atomic. So either an equality or a predicate symbol, because there are no quantifiers there at all, so we don't need to pull anything out. This is if A is atomic. Well, let's write it in a different way. So I'm going to put so if A is atomic, and we return then our output for the process is A. So if A is a negation, not A prime, then what do we do? So then what we do is we find the Prenex normal form of A prime. So let Q1, X1, QK, XK. So we're sort of doing a recursive procedure here. Recursive procedure, let Q1, X1 up to QK, XK for the appropriate K be A prime in Prenex normal form. And we want to return the negation of A in Prenex normal form. So we simply use the fact that for all is not exists not, and exists is not for all not. So wherever there's a for all here, we turn it into an exists, and wherever there's an exists here, we turn it into a for all. So we return.
Is there a quantifier-free formula missing?
There is.
Yeah,
thank you. So we return Q1, X1, QK, QK. What do I think I put a line above in my notes rather than twiddles. Anyway, this just means the opposite quantifier, XK, negation of P. Okay, so this is Q is the other quantifier, different from Q. So notice the sufficient set of connectives. This is just assumed for the input formula. Our output from the result is not going to just be from the sufficient set of connectives. And indeed, the Prenex normal form proposition would not be true. It's only true if you have both universal and existential quantifier, otherwise it's not true. So for the output, we can't restrict to the sufficient set of connectives. That's just giving us easy cases. So finally, if A exists X A prime, that's the only other case of a formula we need to deal with, then let Q1 X1 QK, whoops, QK XK. Oh no, sorry, there's the OR as well. That's the more interesting case. XKB, the A prime DNF, and we return. This one's easy because we simply stick the existential quantifier on front. So we return exists X, Q1, X1. So we just add the existential quantifier on the front, XKB. So that's the easy case. So the more interesting case is disjunction, and in fact, I'm just rubbing off the rules that we're going to use to justify it, but still, never mind, you hopefully made notes of them, and I will. So we're now overrunning a bit for the break, but never mind, we'll have a 15-minute break when we get there. It's not going to take long, so the last case is if A is the disjunction of A1 or A2. So again, so now we let Q1 X1 to QK XK be with B. The A1 in PNF in Prenex normal form, and we let Q prime 1 X prime 1, just to give some names for things. Q prime might not be the same length of quantifiers, so it's a K prime here, K prime X K prime B prime, the A2 in PNF. I'm sorry about the quality of my writing. And now we want to make something equivalent to the disjunction, and we use the distributivity law that allows us to pull both universal or existential quantifiers out one at a time. It wasn't exactly as written in one case, but in any case, it holds. You can always pull out a single quantifier if it's from one side of a disjunction to another. And essentially, we can simply write this is equivalent to the formula. So we return here. We simply pull out these quantifiers in any order, as long as we maintain the respective order within the quantifier prefixes itself. So we can simply, it's perfectly fine to pull out all the unprimed quantifiers first. So QK, XK, and then all the primed ones, Q prime, X1 prime, to Q prime, K prime of XK prime. And then in the inside, we get B or B prime. And you can yourself look at the distributivity laws and think about what else you need and justify that this is a valid step. Anyway, we're done. It's 5 past, so we'll have the 50. Last week I had a vote on whether we want a 15-minute break. I'm not going to have the same, but everybody wanted a 15-minute break, so I would assume it's the same this time, so we start again at 20 past. Hang on, yes. Right, so the last part was this proposition that I've actually just removed from the board, that talked about every formula is equivalent to one in Prenex normal form. We can pull the quantifiers to the outside. This kind of result is called a normal form result. You take an arbitrary formula and you find another formula that has a special form to it, and such special forms are known as normal forms. So we can write this, we can write an arbitrary formula in the normal form of the Prenex normal form with, well, it's called Prenex normal form, but we're going to have other normal form results now that don't have the word normal form in them. But anyway, we can write an inner form in which all the quantifiers are on the outside. One comment I forgot to make about the proof, which is important, in order for this step of listing all the quantifiers together to be correct, it's important that the list of quantifiers here has different variable names from the list of quantifiers here. So of course we can ensure that because, as I said, bound variables, it doesn't matter what you call them. So once you've got A1 in Prenex normal form, get A2 in Prenex normal form, and if there are any variable names that are the same, well, rename them on one side, and then you can form the list. But you have to ensure that your lists here have different variable names. So having dealt with Prenex normal form, essentially that's moved the quantifiers, so that's a normal form involving quantifiers. What we're going to do now for the last part of the lecture is look at normal forms for the formula that we have inside the Prenex normal form, namely for quantifier-free formulas. So for quantifier-free formulas themselves, they don't have quantifiers, obviously, but they may involve any of the other propositional connectives. So what normal forms do we have for quantifier-free formulas? So this is something that I'm sure many of you are going to be familiar with. Anyway, it's just 1 hour of the lecture, and this will be the end of our syntactic manipulations. And next week, having dealt with the syntactic manipulations, we can go on and do something with them. So we can use the syntactic manipulations. So our normal forms for quantifier-free formulas, just to mention them so you know what we're heading for, and they will probably ring bells with very many of you. They're going to be something called negation normal form, conjunctive normal form, and disjunctive normal form. So actually, I said they might not all have normal form in the descriptions, but actually their names do all have normal forming. But they are clearly explicitly all normal form results. And all three normal forms are going to be justified by the same basic logical equivalences. And these logical equivalences are ones involving negation, conjunction, and disjunction, including some we've already mentioned today, but very famous logical equivalences, De Morgan's laws, that tell us that essentially the duality between disjunction and conjunction. And if you negate a conjunction, it becomes the disjunction of the negated items. So these are probably not unfamiliar to anyone, probably familiar. They're called De Morgan's laws. So hands up if these are familiar to you. I expect this is, yes, so this is very basic stuff. And I'm going to add one other equivalence here. A double negation, this is, so this De Morgan's law, this De Morgan's law is peculiar to classical logic. It doesn't hold constructively. The second one here, also this is very famous statement that does not hold constructively, but we're dealing with classical logic. As I said, remarks about constructive logic are just for people who know something about that and are interested in it. So the point is, so these are very known results, but they also allow us, if you think of them going from left to right, it gives us a way, we were pulling quantifiers out of formulas, but with negations, the useful thing to do is push them in the other direction, push them inside formulas, down so that they're just on the end of atomic formulas. So these results from right to left, sorry, from left to right, allow us to push negations inside formulas, and if you get nested negations, then you eliminate them. And actually, it's just a very simple result from this. I'm not going to give a proof, but the notion of negation normal form is a very simple consequence of these. So what we're going to look at now, we're going to look at formulas. We look at connectives, a set of connectives with where we're going to have negation. We're going to have conjunctions. So conjunctions, of course, is and. But when you have and, it's useful to, that's the binary operation. It's useful to also have the zero arity version of a conjunction. So the zero arity of a binary operation is the identity element for that operation. So the thing that makes that and something else is the something else. So the identity for conjunction is, of course, true. Okay. So it's correct to think of true as a zero arity conjunction. And this allows us to make sense of finite conjunctions, which we'll simply write like this. So if we've got n formulas A1 through to AN, we might just write the finite conjunction here. In particular, we allow the case where n is zero. So in the case that it's a zero arity finite conjunction, that's considered to be true. Okay, so those are conjunctions, and we're also going to have disjunctions. So that for disjunctions, we'll have A or B, and again, the identity for a disjunction is false in this case, and this gives us, and from this we can derive the notation for finite disjunctions, I from 1 to n of AI. Okay. Actually, I'm not going to need that right now. I've just realized that I'm going to need it a little bit later. Just to work better with it, I think. It has a kitchen towel on it. Right, so the formula is in negation normal form. So formula A is in negation normal form. Where A is, I'm only going to talk about it for quantity. So we're now looking, we've used Prenex normal form to pull quantifiers on the outside. We're now only for this part interested in quantifier-free formulas. A is quantifier-free. That's part of the definition of negation normal form, if you like, but I mean, I'm only going to ever say it's in negation normal form if we start off with a quantifier-free formula. So a quantifier-free formula is in negation normal form if it contains only the connectives and or the negation, and all negations are in front of atomic formulas. So and negation is only applied to an atomic formula, to atomic formulas. Which means it can only be applied once, because if you've got an atomic formula like equality, not so like x equals y, say, so you can negate that not x equals y, but you can't negate it again because once you've got not x equals y, you're no longer an atomic formula. So not x equals y is not allowed, but of course not x equals y we don't need, because not is eliminated as just nothing. And in fact, the proposition now is that every quantifier-free formula A is equivalent to a quantifier-free formula A n n f in negation normal form. And I'm not going to move the camera for this, but I'll move myself over here anyway, just to refer to this. I'm not going to give the proof, but it's really easy. You simply, whenever you've got a negation, we've only got, well, first we use a sufficient set of connectives. We only include negation and or, which is more than sufficient set, because we don't need both and or if we've got negation. But we include negation and or because we might as well. And it's actually useful to have them both in this case because it allows us to push the quantifiers in. And then whenever we've got negation of an or negation of an and, we push the quantifiers inside like this, and we keep on doing so until we get down to the atomic formulas. And if we ever have a double negation, we just get rid of it. So it's very easy. The other thing you notice about this, if you're computationally minded, there's a simple algorithm here. It's an efficient algorithm. It's linear in the size of the formula in both space and time. And I should have said this about the Prenex normal form as well, that there was also an implicit algorithm there that is, again, linear in the formula. So we've got an efficient algorithm to put an arbitrary first order formula into Prenex normal form to take the quantifiers out, and now an efficient algorithm to take the inside bit and to convert it into negation normal form. Right, so there are two more normal forms to consider, and these are special cases of negation normal form in which the negation normal form is in particularly nice format, particularly simple format. This is conjunctive normal forms and disjunctive normal form. And to justify these, we need two more additional general logical principles, which are just right below the De Morgan's laws. So we're also going to have the distributivity properties, which is that conjunction distributes over disjunction, A and B, or A and C. But also disjunction distributes over conjunction. I think it's a nice thing about logic. So in algebra, you often have one operation distributes over another, like multiplication over addition. It's the classic example. You very rarely have one operation that distributes over another and vice versa. So in logic, we do. So distributivity laws. And these are going to be important for justifying our conjunctive normal forms and disjunctive normal forms, which I'm now going to define. So many of you will be familiar with this, probably, possibly all of you. I don't really want to ask, because if you all put your hands up, then I probably feel that I don't need to give the rest of the lecture, and then which you might be happy with, but in any case, we've only got half an hour left, and let's just check we're all on the same page. So to define disjunctive normal form and conjunctive normal form, the nice way to do it is to start off with the notion of a literal. So a formula is a literal if it is an atomic formula to either an equality or one of our formula or one of our predicate symbols applied to terms. So it's either an atomic formula or the negation of an atomic formula. So the definition of negation normal form could be rephrased as a formula is in negation normal form if it is built up from literals using conjunctions and disjunctions, okay? Because the negation only applied to atomic formulas is saying that negation only occurs to form a negated literal. So we have positive literals and negated literals. Let me look at my notes to see how I do it. So basically, a form is in conjunctive normal form if it is a conjunction of disjunctions of literals, and it's in it's in disjunctive normal form if it's a disjunction of conjunction literals. So the kind of normal form it is refers to the outermost connective, either conjunction or disjunction. So maybe that's, let me see if I still fit to define it in any more fancy yeah, so I did define it in a bit more detail. Let's do that. So a formula is in, let's do this. Well, I'll be consistent with the name. So it's in conjunctive normal form. If it is of the form D1 and so some finite conjunction possibly, but m may be 0, so it may be true. It's finite, some finite conjunction of formulas di, where each di is a disjunction of literals. So where each di is a disjunction of literals. So namely, it's of the form L1 or Ln, say, each Li a literal. So either an atomic formula or a negation of an atomic formula. Just to say there's an important terminology that's often used in computer science for disjunction of literals. These things are called a clause. So a conjunctive normal form is a conjunction of clauses where a clause means a disjunction of literals. But I'm just going to use disjunction of literals here. That's conjunctive normal form. So as I say, conjunctive normal form is a conjunction of disjunctions of literals. Let's just be a bit briefer for disjunctive normal form. So a disjunctive normal form is a disjunction of conjunctions of literals. So the other way around, one has the disjunctions on the outside and the conjunctions on the inside. So again, we're only talking about quantifier free formulas, and let's just write it down briefly. So A is in a disjunctive normal form now. If it is a disjunction of conjunctions of literals. And the last result about the existence of normal forms is that every quantifier-free formula is equivalent to one in conjunctive normal form, and it's also equivalent to one in disjunctive normal form. So proposition for every quantifier-free formula, just write quant dot free formula A there exist formulas A sub theanf and A sub theanf in conjunctive, respectively disjunctive, normal form, such that A is equivalent to A CNF, which is equivalent to A DNF. Okay, so one can always normalize formulas into this very, so an arbitrary formula in negation normal form is so it has nested conjunctions and disjunctions. Here we're flattening things out by the nesting is to depth 2. You either have a conjunction of disjunctions or you have a disjunction of conjunctions. So every formula in conjunctive normal form and disjunctive normal form is in particular in negation normal form, but it satisfies further properties too. Okay, so I just want to end with a proof of this proposition. I'm going to do it quite quickly, but not as rushed as the previous one. I'm going to make it concise. So I'm going to prove this proposition in the case of disjunctive normal form. The proof is very similar, and I'll leave it as an exercise for conjunctive normal form. And once again, I've now rubbed off the distributivity properties which we're going to use in the proof. But that's why I wrote the distributivity properties there, but they're no longer there, but we can remember them. It's actually quite useful that we've already got the result for negation normal form, because we're going to use that. So we don't need to use it, but it does actually simplify life. So proof, we're going to do the construction of A in disjunctive normal form. Now I had these notes, I don't have them in my handwritten notes. I had them in LaTeX, so they're going to be in the LaTeX file. I tried to print them out in the break, and I've been having a difficult relationship with the printer over the last couple of weeks. And anyway, it was very stubborn and it didn't want to print them out. So I can refer to it on my screen if I need to. I'm going to hopefully manage to get by. So I'm actually now curious how I did it, because one way is to actually do disjunctive normal form and conjunctive normal form simultaneously. But I think that's more if you haven't already dealt with the negations. So anyway, we shall see. Rather than talking, let's just get down to it. So we know we can convert. So you don't need to do this, but it's going to be helpful. So first, we're going to convert A to conjunctive normal form. So not conjunctive normal, to negation normal form. So without loss of generality, we assume A. So in other words, without loss of generality, assume A. So assume A is in negation normal form. Okay, yeah, this is going to work. So we've now we've got 3 cases for defining the disjunctive normal form of A. So A DNF is then, well, we've got 3 cases, so it's either negation normal form, so it's either a conjunction of formulas in negation normal form, or it's a disjunction of formulas in negation normal form, or it's a literal, because that's what you get at the end of negation normal form. So let's deal with a literal first. So if A is a literal, in that case, well, then the conjunctive normal form is just A, because a single formula is a trivial case of a disjunct. It's just it's a disjunction of one thing and then a conjunction of one thing. That's just the single formula itself. So in this case, we return A. So if A is A1 and A2, hang on, we're converting to disjunctive normal form, so let's do the easier case first, which is if it's a disjunction. So then we're going to recursively compute the disjunctive normal forms of A1 and A2, and we simply return the disjunction of those, which is still in disjunctive normal form, because the outermost connective needs to be an OR. So we simply recursively compute, sorry, not CNF, DNF, the disjunctive normal form of A1, or the disjunctive normal form of A2. So the third case is the interesting one. So that's if A is a conjunction. So now we can convert A1 to disjunctive normal form, and we can convert A2 to disjunctive normal form, but we would like to conjoin those together with an AND, but we can't because our topmost connective needs to be an OR. So we need to deal with that problem. But to deal with that, we need to look at the structure of the disjunctive normal forms of A1 and A2. So we recursively compute, so let A1 in disjunctive normal form be, so this is going to be some disjunction from I equals 1 to n, say, of some conjunction, of some set of conjunctions from J is 1 to n sub I, because the number of conjuncts may depend on which disjunction we're in. There's a conjunction, it's a disjunction of conjunctions, but they don't all need to be the same length. So then we have Bij, well, Lij, which is literal. So that's A1 in DNF, and let A2 in DNF, we recursively compute that, and that's going to be, again, a disjunction from I is 1 to, let's say, n prime, of a conjunction, of a set of conjunctions from J is 1 to n prime I, of now L prime Ij. And so we've got this big disjunction and this big disjunction, and we need to form the conjunct of that. We need to take the conjunct of that and form and put that in disjunctive normal form. So we could do it using this notation, but I just realized I don't need such to be so detailed here. Actually, it's perfectly fine what I wrote, but actually all we need are the different conjunctions here. So each of these, C sub I is a conjunction of literals, and here C prime sub I is a conjunction of literals. Of course, each one is of the form a conjunction from J equals 1 to n sub I of some literal, but actually we don't need to break down into, I've just realized I don't have my notes, so I just realized we don't need to break them down, we can just use them as they are. So each of these, so C prime I are conjunctions of literals. And then we return what we get by disjoining, from a disjunction that is the same thing as the conjunction of these two disjunctions. And to get that, we use the distributivity law of and over or to distribute the ands inside. So using distributivity, you can work it out. We return the disjunction from over. We need to go from I is 1 to m. We need to consider every pair of conjunct here and conjunct here. So it would be useful to have I prime here, I prime from 1 to m prime, and we consider the disjunction of the conjunctions of Ci paired with Ci prime And this is a big, big disjunction that's got m times n prime conjunctions of literals in it, and it's justified by the distributivity law. Okay, and we're done. It's as simple as that. Now I know some people know this for sure, but anyway, there's something very horrible about this. Does anybody know what's horrible about this? It's related to NP. So what's horrible about this, if you implemented it, this algorithm is exponential in time and in space. It constructs a formula that's exponentially larger than your starting formula, and it takes and it necessarily takes exponential time to do so because it needs to write the formula down. And as far as people know, there's no way of avoiding this, because if you could do this in polynomial time, then there would be a polynomial time solution to the NP problem. Okay, so as far as we know, the conversion to disjunctive normal form or to conjunctive normal form is necessarily an exponential time and space operation. Whereas negation normal form is very efficient. So I always find it surprising. I mean, you can work out why this is the case, because we're sort of doubling things in size essentially here, but I mean, worse actually, but well, no, I guess. Anyway, you can work out why it's the case, but still, when you see it, it looks kind of innocuous, and so for me, it's a little bit of a shock always that this is the case. Right, good. Well, that's everything for today. Let me stop the recording